Assalamu alaikum and good morning. In the previous lesson, we have looked at the calculations involving Kc. Kc is the equilibrium constant in terms of concentration. Today, we're going to look at the equilibrium constant in terms of partial pressure, Kp. Before we look at how to calculate partial pressure or what a partial pressure is, we first look at mole fraction. The mole fraction of a gas is the ratio of moles of a particular gas to the total number of moles of gas present. So this is like if I use our classroom as a scenario. If I want to talk about the mole fraction of boys in the class, I would take the total number of boys over the total number of students in the class. So that's the mole fraction for boys. And similarly, I would do the same for mole fraction of girls. For gases, we look at the mole fraction as number of moles of gas X, so that's the particular gas that we are interested in, over the total number of moles of all the gases. And there you have the mole fraction. Okay, so we will put that aside. And now we're going to look at the partial pressure. The definition of partial pressure of a gas in a mixture is the pressure that the gas would have if it was in the container all by itself. So I think it's easier to show this visually or in diagrams, right? Imagine you have a container containing a mixture of two gases, gas A and gas B. You can't see it in your notes unless you print out your notes using color printed. You would be able to see that in this container, there's a combination of gas A and gas B, which is green and blue respectively, okay? If I want, and we all know that pressure is based on the frequency of the gas molecules hitting on the walls of the container. The higher the frequency of these gas molecules hitting, knocking onto the wall of the container, the bigger the pressure is. Partial pressure is the pressure that would be exerted only by one type of gas. So for example, in this container, I want to know what is the pressure that is exerted by gas A only. Okay, I can't just say, oh, it's half, because sometimes the number of particles of gas A is not equal to the number of particles of gas B. So here we've got more gas A than gas B. If I want to know the partial pressure of gas B, that means in this container, I want to know how much of the total pressure was caused or was exerted by my gas B. All right. So for example, we've got, I think the number of circle represents the pressure. So each circle is one pressure. The total pressure is 11 Pascal. Okay, so we're just going to use an easy number, right? And so 3 of them out of the total pressure is the partial pressure of gas B, whereas the 8 Pascal represents partial pressure of gas A. Okay, so in total, the total pressure in the container is equals to the partial pressure of gas A alone. If it was alone in the container, of course, it's impossible or difficult for us to separate. If I have a container mixture of gases, then I want to separate gas A and gas B. It is not possible to do that, okay? So what is true for all the system, okay, gas system, is that if you add the partial pressure of gas A plus the partial pressure of gas B, you would get the total pressure of the system. All right, so this is a hopefully a useful and helpful diagram to help you understand the concept of partial pressure. Okay, I've basically already explained to you, if a mixture of gases contains two different gases, then the total pressure will equal to the sum of the two partial pressures added together. So if you have more gases in that system, you would have to add each of the partial pressure together to get the total pressure, right? Usually, the one that we can measure is the total pressure. All right, it's not easy to calculate partial pressure. But what we can do is use a formula to find the partial pressure of any gas inside a system. We take the mole fraction, which makes sense, right? How much of the proportion of gas you have in that container belongs to gas A times by the total pressure. So it's like a proportion of gas A times by total. That means you know how much gas A would contribute to the total pressure in a way, right? So you would imagine the more particles, the more molecules of gas you have of that type, then the partial pressure would also be high. Okay, the bigger the number of the gas molecules, the bigger the partial pressure. Okay, so this expression or formula will be useful for you to apply later on in questions, but the most important thing is that partial pressure A plus partial pressure B is equals to the total pressure you have in that container. If you have three gases, partial pressure A plus partial pressure B plus partial pressure C is equals to the total pressure in that container. Now we look at the equilibrium expression Kp. It is similar to your Kc, except that now we are looking at partial pressure instead of concentration. When we're talking about pressure, we should only be looking at reactants and molecules that are in gas state. So here we ignore solids, we ignore liquids, we ignore aqueous substances. Whereas for Kc, we can do aqueous, we can do liquid, we can do gas, but not solid. Okay, so for both Kc and Kp, we cannot apply solid for this expression. We cannot apply this expression to solid because solid doesn't have concentration, solid doesn't have partial pressure. Okay, so here's an example. Our equilibrium system is the formation of ammonia from nitrogen, from the combination of nitrogen and hydrogen to form 2 moles of ammonia. So Kp is now in terms of partial pressure. In Kc, our concentration, we use the symbol square bracket. We represent concentration as square bracket. Here we use a small letter P. I know sometimes in text you will see it as italicized, but in the exam you don't have to, right? Now, okay, so P stands for the partial pressure of your product. So in this case, we have NH3. Now for partial pressure, there is no bracket. The reason actually, there's no clear reason as to why they don't use bracket, okay? But we just write down P and then the square, because there's 2 moles of ammonia being produced, the square, you will see sometimes they write down the square after NH3, but I personally like to write down the square next to the letter P. The reason for this is maybe sometimes it gets confusing. You will think that the 2 is a charge, but it's not wrong. Okay, what is wrong is if you write down square bracket for partial pressure, that is wrong. You must only use P as your symbol for partial pressure. Okay, so that's your product done. Over the partial pressure of your reactants, P and 2. You can include your state symbols or you can leave it out, that's fine. Times by, we don't usually write down the times, the multiplication symbol. P, the partial pressure of hydrogen raised to the power of 3 because the mole ratio of hydrogen is 3. Okay, so each P represents the equilibrium partial pressure. So that is something important for all of us because we do not take the initial pressure, we do not take the final, we take the partial pressure at equilibrium. Each substance in Pascal. So each P represent Pascal, but there are also sometimes in question, you will see atmosphere, ATM, and there's no problem with that. Okay, the powers are the mole ratio in the equation. So the powers I'm referring to is this: 2 moles of ammonia and 3 moles of hydrogen. The units of Kp depends on the form of equilibrium expression. So we work out the units of Kp in the same way we work out for the units of Kc. Let's see. Okay, so we're going to look at example 1. Write down the expression, equilibrium expression Kp and the units for this reaction. Right. So I am going to choose something that is bright. Okay, so Kp is equals to the partial pressure of products NO2 squared over the partial pressure of my reactant N2O4, and there's nothing else. And it's also the mole ratio is also 1. The stoichiometry number is also 1. Okay, it doesn't say my units whether it's in terms of Pascal, so I'm going to add in terms of PA. Okay, right, units. Top part, I've got Pascal square because I have squared the partial pressure of my NO2. It is power over Pascal to the power of 1. So if I cancel this out, then I am left with just Pascal. Okay, next, before I start writing down my Kp, I must always inspect my reactants and products. Fe is a solid, not included. H2O is a gas, fine. Fe3O4 is a solid, not included. H2 is a gas, is fine. So when I write down my Kp, it is the partial pressure of my hydrogen product and only hydrogen raised to the power of 4 over the partial pressure of my reactant. In this case, only H2O is included because they are gases, because it is a gas, raised to the power of 4 as well because of the stoichiometric number. Okay, so I'll just highlight that. And then these ones are solid, so therefore they're not included in the expression. For units, each P is Pascal, but since my partial pressure is raised to the power of 4, I've got Pascal to the power of 4. Bottom one is also Pascal to the power of 4. They cancel out nicely, so that means my unit is no units. All right. So there's nothing new there. All you have to do is just change the representation. When you are dealing with Kc, you use square bracket. When you are dealing with Kp, you use P. Okay. Next example. A mixture contains 0.2 moles of nitrogen, 0.5 moles of oxygen, and 1.2 moles of carbon dioxide. If the total pressure is 3 atmosphere, what are the partial pressures of the three gases? So that means the partial pressure must be of each individual gas. So I should start with N2, O2, and CO2. To find the partial pressure, I need mole fraction times total pressure. Okay, so you can see that my total pressure is given as 3 atmosphere. First, I need to know my mole fraction. Well, you can do this all in one line. Mole fraction is the proportion of each gas out of the total number of gas. So my total number of gas and total is when I add up all the number of moles of all the gases. 0.2 for nitrogen, 0.5 for oxygen, and 1.2 for carbon dioxide. That should give me 1.9. Yes, okay. So mole fraction for nitrogen is 0.2 over 0.9 because there are 0.2 moles of nitrogen in this mixture. For oxygen, it's 0.5 over 1.9. Sorry, my mistake. It should be 1.9. And carbon dioxide is 1.2 over 1.9. So you can see that carbon dioxide has the biggest proportion. You would imagine the partial pressure caused by carbon dioxide will also be the highest or the biggest. So partial pressure, just to change color, partial pressure P. Okay, so you take mole fraction times by capital P total. So that's your total pressure. So in this case, is it easier to use decimals? Okay, maybe we will just use fractions. 0.2 over 1.9 times by 3, 0.5 over 1.9 times by 3, and 1.2 over 1.9 times by 3 for carbon dioxide. And this is your mole fraction. And this is your P total. So you just have to work it out. You should get 0.315. Now your question is, what is the unit of partial pressure? The same unit as given in the question. Okay, here we have atmosphere, so we write down as ATM. 0.5 over 1.9 times 3 should give you 0.789 atmosphere. And then 1.2 over 1.9 times 3 is 1.89 atmosphere. Okay, to check if your calculation is correct, you add all of them together and it should give you 3 atmosphere. Okay, if you add the partial pressure of each gas should be equals to 3 atmosphere, which is the P total. All right, so that's a short exercise, which is nothing too complicated on how to work out the partial pressure of each gas molecule, given the number of moles and given the total pressure of the container or the system. So if you want to copy this down, you can pause here and I will move on. to the calculation of Kp. So this will be example 3 on page 12. In the reaction where you have sulfur dioxide combining with oxygen to give you sulfur trioxide, the equilibrium partial pressures at constant temperatures are given. So you see that the key word is equilibrium partial pressure. So that means everything is nicely given to you. All you have to do is start writing down the Kp. Is there a numerical answer to this? There's no numerical answer. Okay. So Kp expression, partial pressure of product SO3 raised to the power of 2 over partial pressure of SO2 raised to the power of 2 times by partial pressure of oxygen raised to the power of 1. Just make sure that each reactants and products are in gas state for you to include them in the expression. Next, you don't have to do anything. You just have to sub in the numbers correctly. And then make sure you don't forget to square whenever a square is needed. And your answer, oh, I'll talk about the units first. Let's talk about the units. You are given the units of pressure, partial pressure in terms of Pascal. So you just follow through. Top part of your expression, you've got Pascal square because we raise the power of sulfur trioxide to the power of 2. Bottom over Pascal 3. Okay, because you've got 2 here and then you just have 1 here. So what happens is that they will cancel out 2 and this becomes just 1. And you bring that up. Pascal now becomes Pascal to the power of -1. Okay, so I will let you try. And you should get your Kp answer as 9.14 times 10 to the power of -6 Pascal to the power of -1. Okay. You can pause here if you want, but I will continue with the next example. Nitrogen reacts with hydrogen to form ammonia. The pressure exerted by this mixture of hydrogen, nitrogen, and ammonia at constant temperature is 2 times 10 to the power of 7. So you can see that the pressure exerted by this mixture, that is the keyword. That means it's the total pressure. Okay, that's your pressure total. Under these conditions, the partial pressure, now it's mentioned, the partial pressure of nitrogen is 1.49 times 10 to the power of 7. The partial pressure of hydrogen is 0.4 times 10 to the power of 7 Pascal. Calculate the value of Kp for this reaction. Okay. So we know the partial pressure of nitrogen, right? Although strictly speaking, the questions should say or mention at equilibrium, right? But since it doesn't, we're going to just assume that it is the partial pressure at equilibrium. So we know the value for nitrogen. We know the partial pressure of hydrogen as well. We don't know the partial pressure of ammonia. And if we don't know this value, we can't carry out or we can't calculate the value for Kp of this system. All right, so what can we do? We go back to this expression where P total is equals to partial pressure of nitrogen plus partial pressure of hydrogen plus partial pressure of ammonia. Imagine these 3 gases are in the system, in the mixture, okay? So if we want to find partial pressure of ammonia, PNH3, we have to take the P total minus P nitrogen minus P hydrogen. Okay, so that's 2 times 10 to the power of 7 minus 1.49 times 10 to the power of 7 minus 0.4 times 10 to the power of 7 Pascal. Okay, so you work out and be careful because when you put in the numbers in your calculator, you need to put them in bracket. Okay, so I want you to work out the partial pressure of ammonia. I will help you set up the Kp expression. Kp is equals to the partial pressure of the product, which is NH3, raised to the power of 2, over the partial pressure of your reactants, which is nitrogen, raised to the power of 1, times by the partial pressure of hydrogen, which is to the power of 3. If I work out the units, it should be Pascal square over Pascal 4. So we've already done this just now. Yeah, 3 plus 1 is 4. Did we do this just now? Oh, we didn't. We didn't work it out. We didn't work out the units. Okay. So what happens is that the 2 cancel out and we're left with 2 Pascal at the bottom. Okay, and then we carry this up. So you will get P 2 minus, sorry, 2 minus. Okay. Sub in your numbers. You already know the partial pressure of nitrogen. You already know the partial pressure of hydrogen. Now you are left with the partial pressure of NH3. Okay, from here. So I will leave you to work out and get this number. Okay, please, if you cannot get the numerical number in your notes, please let me know. Okay, please say something, right? Sometimes it's just a matter of calculator or calculation error. You incorrectly press in the wrong number, but please say something. All right. Okay, so if you want to pause this, you can pause here and I will move on to the next question, example 5. Now, I noticed that example 5, actually, I do not need this whole table. So I myself was confused. Okay. Why? I'm given the partial pressure already. Okay. So this table is if I wasn't given the partial pressure. I don't need that column. And I also don't need this column, right? I'm given this information. The information below gives the data for the reaction of hydrogen with iodine at 500 degrees Celsius. Deduce the partial pressure of the iodine at equilibrium, and then you calculate the value of Kp. Do I have space? No. Right. I don't know the total pressure. I know the partial pressure of hydrogen at equilibrium and hydrogen iodide at equilibrium. Okay, so make sure you cancel this. That is not supposed to be there. So very sorry to make you cross out or cancel things on your notes. Okay. The first thing is I need to know the total pressure. If I know the total pressure, at least I can add up. I can work out hydrogen plus hydrogen iodide plus iodine. All right. However, though, I know initially the partial pressure of my hydrogen and iodine and hydrogen iodide. I can add them up to get my total pressure. And because my system is a closed system, initially and until it reaches equilibrium, I know that my total pressure at the start and at the end at equilibrium would be the same. I cannot increase the pressure or decrease the pressure because it is a closed system. I will change the composition of the partial pressure, but the total pressure I cannot change. Okay, so you can add a note. Since it is a closed system, the total pressure at initial should equal to the total pressure at equilibrium. Okay, because at the start of the reaction already, my system has to be in a closed system, because if it's not a closed system, they will never achieve equilibrium. My products will keep escaping and eventually I will run out of reactants, right? So what I can do here is first I take the initial total pressure by adding the partial pressure of hydrogen at initial plus partial pressure of iodine at initial, and that is, let me make this bigger, 7.27. Oh, I have a typo there. It should be times 10 to the power of 6, not 8. Okay, the initial partial pressure of hydrogen should be 7.27 times 10 to the power of 6. Okay, continue. Plus iodine is 4.22 times 10 to the power of 6. So now since both of them are to the power of 6, what I like to do is I just add 7.27 plus 4.22 and I get 11.49 times 10 to the power of 6 Pascal. Okay. And then if you want to change that to 1.149 times 10 to the power of 7, they are the same. At equilibrium, it should be partial pressure of HI as well. Okay, you do not ignore the HI, but since it's 0, that's why I forgot to add it in. Okay, at equilibrium, the pressure total must also be the same, but this time I'm adding, oh, sorry, it shouldn't be big P, it should be small p. Partial pressure of hydrogen plus partial pressure of iodine plus partial pressure of hydrogen iodide. So the P total is the same at the start and at the end. So you just add in the number. For hydrogen, it's 3.41 times 10 to the power of 6 plus iodine is what we want to find. You can make that as your X. Partial pressure of hydrogen iodide is 7.72 times 10 to the power of 6. You work out the partial pressure of iodine at equilibrium. Do I have a number? Sadly, I do have a number. Actually, I can do it now. 11.49 minus 3.41 minus 7.72. So that is 0.36. Is that right? 11.49, 3.41, 7.72. Okay. 0.36 times 10 to the power of 6. And this is in pressure, so Pascal. So that's only part 1 of the question, where it requires you to work out the partial pressure of iodine at equilibrium. Okay, so this is the partial pressure of iodine. The second part, which is part 2 of the This question wants you to calculate the value of Kp for this reaction, including the units. Okay, moving on. Kp, I have to refer to the equation. Where's the equation? There. I need to take the partial pressure of the product raised to the power of 2 over the partial pressure of hydrogen times by the partial pressure of iodine. Don't forget the mole ratio. You make it as the power. Partial pressure of hydrogen, partial pressure of iodine. Okay, and then you work out the numerical units. Top expression, PA square, bottom expression, also PA square, okay? PA times PA is just PA square, and they cancel out. So there is no unit for this Kp. Okay, so I don't know if you can see the working, but please work out your Kp should be 48.5 no unit. Okay, please work it out and check if you can get the numerical answer or not. If you cannot, please let me know. Right, you can pause here and I will move on to the last example, I believe. Okay. Example 6 is looking at the system of ammonia and hydrogen, nitrogen and hydrogen to form ammonia. 1 mole of nitrogen and 3 moles of hydrogen are added together and the mixture is allowed to reach. So that means they haven't reached equilibrium yet. They are initial values. Okay. At equilibrium, 20% of the nitrogen has reacted. If the total pressure is 2 atmosphere, what is the value of Kp? Okay, so there are a lot of things happening here. I would like to deal with the number of moles first. Okay, don't go straight. Oh, I know the total pressure at atmosphere, so I can find the partial pressure. No, we always start with the number of moles. So I believe this label is wrong because we are dealing with number of moles and in mole. So please change that. Okay. Right. Initially, 1 mole of nitrogen. So that means 1 mole of nitrogen reacts with 3 moles of hydrogen and no mention of the number of moles of ammonia, 0 initially. Okay, they are then allowed to reach equilibrium, right? At equilibrium, 20% of the nitrogen has reacted. So that is your second row, the reacted and produced row, and it says 20% of nitrogen has reacted. Okay, 20% of nitrogen is 0.2. Sorry. Okay, so that means 0.2 moles of nitrogen has reacted. I don't know anything else, any other information. I don't want to look at the total pressure. These are the only information that I know. But the middle row is powerful. If you know at least one value for either the reactant or the product, and you also know the balance equation of this system, you can use mole ratio to find the values of other unknown molecules. Okay, so let's see. Now I've already got my value for nitrogen. So if I want to work out for hydrogen, I will just write down that they have a 1 to 3 ratio. And if I have used 0.2 moles of nitrogen, how many moles of hydrogen would I need? So that's just 0.2 times 3, 0.6. Next, if I know I use 0.2 moles of nitrogen, how many moles of ammonia would have I produced? So the ratio is 1:2. 0.2 nitrogen X is the number of moles for ammonia, and it turns out you would have produced 0.4 moles of product, or in this case, ammonia. Next, at equilibrium, I don't know if you still remember this from the first part of our calculation from KC. If you want to find the number of moles or concentration at equilibrium, you take initial minus reacted. So that's 1 minus 0.2. I've got 0.8 moles of nitrogen at equilibrium. I am nowhere near my partial pressure, okay? Please bear in mind that I am not at partial pressure already, and that is fine. We're just doing things one step at a time. Same thing for hydrogen. I need to take the initial mole of hydrogen minus the reacted mole of hydrogen. If I'm looking at hydrogen, I need to focus on just hydrogen, okay? I cannot do this. I cannot just say, oh, if I have 0.8 moles of nitrogen at equilibrium, I just multiply that by 3 to get my number of moles of hydrogen at equilibrium. No, that is a big no. Okay, so to find hydrogen at equilibrium, you must take I minus R. So that's 3 minus 0.6. I've got 2.4. And lastly, for my product, especially if I don't have anything at the start, I cannot take my initial minus how much I have produced. Obviously, that would be a negative number. So for products, we usually add on I plus P will give me the value at equilibrium. So that's just 0.4. These are my number of moles. That's why I tell you it is important for you to label your table. Of course, in the exam, I am not expecting you to prepare an elaborate table like this. No, just quickly write down IRE and then quickly write them down in columns and row, and then you work from there. Even if you don't have lines, that's fine, as long as you have a system of organization. You don't want things to be all over the place, right? Next, then I want to find partial pressure. Partial pressure is equals to mole fraction times P total. First, I have to work out my mole fraction. Before mole fraction, I need to know the total number of moles, and total is 0.8 plus 2.4 plus 0.4. That should give me 3.6 mole. So I know I'm talking about the number of moles. So if I want the partial pressure, it's 0.8 over 3.6, that's my mole fraction, times by total pressure is given 2 atmosphere. Okay, and then for hydrogen, it's 2.4 over 3.6 times by total pressure. And lastly, for ammonia, it's 0.4 over 3.6 times by total pressure, which is 2. Okay, whatever numbers you work out here, when you add them all up, it should be equals to 2. No more, no less, because that's your total pressure. You cannot have more total pressure or less total pressure than the number that is given to you. Okay, I'll let you work that out. And then your KP for this system, I feel like this system comes up a few times already, okay? partial pressure of the product over partial pressure of the reactants, and 2 partial pressure of the other reactant, hydrogen raised to the power of 3. Okay, so I want you to work out the units and the numerical number. Okay, so later on, give me the numerical number to 3 significant figures. So we'll see. Please, I don't have the answer right here. Okay, so please try this out and then check out if your answer matches with the answer I have in the forms later on. All right. Don't forget your units. I will just leave it here. Units is important. You have to work it out. They give you in terms of atmosphere. So you should have it as atmosphere. Okay. If there is unit. All right. So that's all the example for KP. I want to, what do I want to do now? Okay, I will take a break from the notes. I want to bring your attention to your exercise 7.1. Okay, if you have printed out exercise 7.1, you can take it, put it in front of you now. If you don't have it, you can pause the video, print it out, or you can refer to it on your device first. But I want to work with you question 3B. Okay, so you can pause first if you don't have the materials in front of you. If you need to take foolscap paper or calculator, you will need your calculator for this. Okay, the reason why I want to bring your attention to this is because this is the example that I did not give in the notes, in your notes, but it's the kind of question that they ask in the exam. Okay. Okay, the carbon monoxide for use in the production of methanol may be formed by reacting carbon dioxide with hydrogen. So this is your reversible dynamic equilibrium system, right? You usually write down Kc or Kp only for reversible system. Okay, if you don't have it in a reversible system, it's not in a dynamic equilibrium, the system is not closed, then you wouldn't be able to find the constant Kc. What happens is that your reactants will evaporate, your products will evaporate, then you wouldn't have a continuous reversible reaction. It will come to a stop. In theory, equilibrium does not stop. They continue to react. Forward reaction happens, reverse reaction happens, and this continues in a loop because you always have a certain amount of reactant and a certain amount of products, and the forward and reverse rate is continuous. Okay. Anyway, moving away from that and back to this question. This time, you notice that they have given us the Kc. In the examples that we did, all our Kc values are the one that we have to work out ourselves. Okay, so just leave it there for now. Okay, a mixture containing 0.70 mole of carbon dioxide and hydrogen, 0.30 mole of carbon monoxide and water was placed in 1 dm cube of flask. So remember, we are dealing with Kc, so we want concentration. At the moment, we just deal with number of moles first, okay? But don't forget that information later on. is allowed to come to equilibrium at 1200 Kelvin. Calculate the amount in moles of each substance present in the equilibrium mixture at. Okay, so I only know the initial. I need the reacted and produced in terms of products, as well as at equilibrium, but I do not have any other information. Now you notice that this is also the first example that we've done where the product is not zero. Okay, so there is some sort of product that you started with. Now, since I'm stuck, I don't have any other information. I know the volume, but again, the volume does not help me much. So since my Kc is given, I will just write down the Kc on the side. Okay. Kc is equals to the concentration of product, which are carbon monoxide and H2O, over the concentration of carbon dioxide plus H2. Okay. Now, again, that's not much of a help. All right. I'm not here to find Kc. I am here to find number of moles. Okay. So I have to work in reverse because I know that my Kc is equals to 1.44. No unit, okay, because you can see that mole per dm cube cancels top and bottom. Okay, what I can do is I am going conveniently, okay, that my volume is 1 per dm cube. Okay, so I will have another row, equilibrium concentration. Okay, just in case, but since the volume is 1 dm cube here, so it doesn't have any effect. Okay, if you forget that, you'll still be fine. Now I am stuck, but what I can do is I can let the number of moles of CO2 reacted be X. Y. Okay. No, I mean Y as in WHY. So you see here, I will make my number of moles of CO2 reacted as X, because remember the special thing about this middle row? If I know one information about any of the reactant or the product, and I also know their stoichiometric relationship, that is their mole ratio, I can find the other values for the reactants and products, only for reacted and produced, okay, not for equilibrium. So if my equation is telling me 1 mole of carbon dioxide would have reacted with 1 mole of hydrogen to form 1 mole of product, carbon monoxide, and 1 mole of water, H2O. It's H2O gas. So that means if the number of moles of carbon dioxide reacted was X, the number of moles of hydrogen reacted would also be X. Sorry. Because carbon dioxide and hydrogen is 1 to 1. Right? That's my reactants. What about my products? Same thing. Carbon dioxide and carbon monoxide has a 1 to 1 relationship. So that means the product that I would produce would also be X. Same thing. CO2 and water, H2O, is 1 to 1, therefore X. Right now, it looks like it doesn't make sense, but just bear with me, okay? We are now working out the number of moles of these reactants and products at equilibrium in terms of X, because that's the only way. We don't have any other hints or any other value given to us. Okay, so what happens at equilibrium? E is equals to initial minus reacted. So for carbon dioxide, that would be 0.70 minus X. For hydrogen, same thing, initial minus reacted, 0.70 minus X. For products, equilibrium is equals to initial plus produced. Okay, so that's 0.30 plus X. Same for H2O. At equilibrium is equals to initial plus produced. So that's 0.30 over X. Now this, we are still, why do I have that? It should be 0.30 plus X. Okay. I feel like I should put this somewhere here so that it doesn't end up at the very bottom. And then you will wonder, why do I suddenly have X? Okay. Next, concentration is equals to number of moles. So you see here, initial moles, number of moles reacted, number of moles of equilibrium. I know this is a long question. To find concentration, which is what you should be using in KC, C is equals to N over V. N in mole, V in dm cube. Nicely enough, this question gives you the volume in terms of dm cube already. So it's just divide by 1. So for concentration, I'm running out of colors. 0.70 minus X over 1. 0.70 minus X over 1. So that's the concentration of your carbon dioxide and hydrogen. 0.30 plus X over 1. 0.30 plus X also over 1. So if you just cancel them, everything, the 1 will just go away. Okay, so then I substitute these numbers into my KC because I already know my expression for KC. Concentration of products goes on top, concentration of reactants at the bottom. So it's time for us to put in numbers. KC is 1.44 given in the question. If you're wondering where I got this 1.44, it is here. Okay. Next, concentration of carbon monoxide would be 0.30 plus X times by 0.30 plus X over the concentration of my reactant CO2, 0.70 minus X times by the concentration of my hydrogen, 0.70 minus X. Now, for your syllabus, you do not have to solve quadratic equation. No solving of quadratic equation. So do not open the brackets. If this kind of question comes out, I can assure you that the numbers will be nice. That means, you see this? 0.30 plus x times by 0.30 plus x, that can be written down as 0.30 plus x square over, again, 0.70 minus x times by 0.70 minus x. You can simplify that to become square. All right. So I don't know how fast you can do this, but because top and bottom is raised to the power of 2, to cancel that out, I take the square root of 1.44. Is that okay for you? If I just add on a another step here, which I think I shouldn't, because I hope, I'm sure that everyone can see it. It's the same. Okay, so if I want to cancel out this square, this power, I multiply it by half, or I take the square root of on both sides. So if I take the square root here and I take the square root here, this will cancel out. Okay, if we cannot see that, that is from a mathematical point of view. It's not chemistry. Okay, I will not teach that. Okay, so square root of 1.44 is 1.2. Ah, that's nice. 1.2 times by 0.70 minus x, 0.30 plus x. Okay, you open the bracket and you will get a nice expression in terms of x. You should get your x as 0.25. Okay, can you please work that out? Now, I want to go back to this question because it feels like I am doing maths instead of chemistry. The question is, calculate the amount in moles of each substance present in the equilibrium mixture. Let's go back to X. If you see here, I have let X to be the number of moles of CO2 reacted. I should have labeled this just now. So bad. Okay. But the question is asking for the value at equilibrium. Okay. So to find, do I have, oh, okay, I have still space there. To find number of moles at equilibrium, you have to sub in. At equilibrium is 0.70 minus x, and that's the same as number of moles of hydrogen as well. Okay, number of moles of products, H2O, at equilibrium is 0.30 plus x. So it works for both. Your x is the one that you just found from the long algebra process, long algebraic process. Okay, so that answers your question. Calculate the amount in moles of each substance present in the equilibrium mixture. Don't leave your answer in X because that's not answering the question. They want at equilibrium. Whereas your X is for the one that is reacted. Some students ask me, what if I make my number of moles at equilibrium X? Yes, you can do that as well. Okay, No problem with that, of course. But if you come to a point where you have to solve a quadratic expression, that means it's wrong. Okay? Do not try to find a way that doesn't require you to solve quadratic equation. Okay? I don't know how I'm going to zoom this, or whether if you could see it. Maybe I will zoom to the first half of the screen, which is this. Okay, so if you want to stop here or screenshot this, you can take a screenshot now. And then at the bottom is how you find n at equilibrium. You have to sub in your x. This question is not asking for Kc. It wants us to find the number of moles at equilibrium given Kc. So this is a totally different example or a totally different approach from the questions that we have done in your notes. All right. Okay, so please work this out. Do not just assume that your answer will be the same as mine. Who knows? In the middle of the process, you are digesting this and you are working out the numbers and there's a mistake that I made. Please let me know. And that is all for today. I will give you one question as homework to do from this exercise 7.1. Just wait for my instruction. And don't forget to fill in the questionnaire in forms. Okay, so there are questions for you to do in forms that needs to be submitted today. Your homework, I will give you 1 day to do it. Okay. All right. Assalamu alaikum and thank you, everyone.